Okay, now we'll continue with point number 3. In case my mic becomes too noisy later, please let me know in chat. Then maybe I have to rejoin the meeting. Okay, point number 3 on the true or false section. Okay, the length of the vector Ka is equal to K times the length of A, where K is a real constant. Okay, do you think this is true or false? Okay, on the left is length of vector Ka. Okay, on the right is K times the length of vector A. Okay, so do you think this is true or false? Your response in chat. Okay. To those who say it false, under what situation would it become false? Under what situation will it become false? Yeah, it's false when K is negative. Yeah, good. It's false when K is a negative number. Yeah, because if K is a negative number, on your right hand side, you're going to get a negative. Because length is always positive, this one is guaranteed to be positive. So if K itself is negative, then the entire right hand side becomes negative. But then the left hand side is a length which is always positive. So you end up having positive equals negative, which is impossible. A positive number can never be equal to a negative number. Right, so this statement is actually false. This statement is actually false. The answer is false. This statement is only true provided that K is positive. So in general, if we look at this statement, this is a false statement because here they say K is real. This equality that doesn't always hold when K is real. So to consider the statement under point number 3 itself, it is a false statement. Now this statement only becomes true it is true only when K is more than or equal to 0. It is true only when K is more than or equal to 0. Now, what is the true relationship then? If we still want to consider all possible real values of K, including the negative one, what should be the true relationship? Okay. So, for the case when K is negative, which means K less than 0, when K is negative, the length of K times A is actually negative K times the length of A. This will be the correct relationship when K is negative. Okay, so let's take an example. Let's take an example here. If I have this is a vector K, and I have negative 2A, which goes the opposite direction. So if A, for simplicity, let's have A being length 1 unit, then negative 2A will have length of 2 units. Okay, so how can we get length of 2 if we want to use a number minus 2? Okay, so we can get length of 2 by taking, okay, so this means length of negative 2A is actually negative 2 times length of A. Okay, and that will give us 2 times 1, which is 2. So yeah, so what Shruti says in chat is correct. If we want to include both positive and negative, both the possibilities of K being positive and negative, the true relationship is for any K in R, the length of Ka is actually modulus K modulus A. And this is a correct relationship. This can be further broken down into k times modulus A if k is more than or equal to 0, minus k times modulus A if k less than 0. And so this is a correct relationship that is applicable to all real values of k. So some examples on how this can be applied. For example, if you are given that length of B is, let's say, 3 units, okay, then the length of 4B, it will be modulus 4 times length of B, which is 4 times 3. That will give you 12 units. And then there is a length of minus 5B. The length of minus 5B will be modulus minus 5 times length of B. Modulus of minus 5 is actually just a 5. The length of B is 3. So you get 15 units. Also notice that you always have positive answers because lengths are always positive. So the first pair of modulus here is the usual modulus. This is the usual modulus. While the second pair of modulus is the length. And so when modulus is applied on a number, it's a usual modulus. When modulus is applied on a vector, it means the length. And so this is the true relationship. And the true relationship is you need a modulus there. And if you want to include the possibilities of k being positive and negative. Now move to point number 4. Okay, length of A plus B is equal to length of A plus length of B. Do you think this is true or false? Your response? Do you think this is true or false? Okay, it is false. Yeah, it is false. But this one is actually quite obvious. It is false in general. In general, it's false. In general, it's false. Under what situation will it become true? A plus B is equal to A plus B is true only when wait, what do you mean by both positive or both negative? These are all positive numbers. This is a length. This is a length. This is a length. Length are all guaranteed to be positive. Wait, I think you guys are confused. A and B are vectors. You can't say a vector is negative. A vector is neither positive nor negative. A vector only has length and direction. So think carefully, what is the word to use there? Yes, good, same direction. Yes, same direction. It's true only when A and B have the same direction. So this is the answer. Yeah. So don't get confused. A and B are vectors. We never say a vector is positive. We also never say a vector is negative. A vector is not a number. Right. So modulus of a vector means the length of a vector. We have been using the modulus symbol from the very beginning of the chapter. But if you're asking this question now, this is very worrying. Modulus of a vector refers to the length. It no longer means the usual modulus. All these modulus are notations for lag. It's not the usual modulus. Okay. Yeah. So it, this this equation is only true when A and B have the same direction, which you can see. If I have the vector A is like this, vector B is connected end to end, and then my vector A plus B will be from the very beginning until the very end. Right. So in this case, only in this case, my length of A plus the length of B, which is the purple length plus the red plus purple, red length plus purple length, it will be equal to green length. Only in this situation will it be true. In any other situations, when A and B have different directions, that equality will not be true. Right, so another example, if I give you a vector A pointed this way, vector B pointed this way, and then of course my red length plus purple length, it will be definitely longer than the resultant A plus B. Red length plus purple length, it will be longer than the green length. Which means length of A plus length of B will be greater than length of A plus B. When A and B have different directions. Okay. Right, so the true relationship is for any two vectors, A and B, and with any length and any direction, it is always true that the length of A plus the length of B is either longer than or equals to length of A plus B. Right, so this is the true relationship. And equality holds when, so you can only write equal instead of the inequality. Equality holds only when vector A and B have same direction. If we are not sure about the directions of A and B, then the relationship that is guaranteed to be true is actually more than or equals to. The two separate lengths added up, it will be longer than the length of the resultant, which you can easily see from the triangle diagram up there. Length of A plus length of B is definitely longer than the green length. Okay, so all these true or false statements is just to test you on an understanding of the concepts. In that exam, of course, there won't be any true or false questions. This is just for your better understanding. And also in point number 3, we learn how to deal with length of the vector Ka. Right, so when you have length of vector Ka, you can just distribute the modulus over the K and the A. Of course, the two modulus will then have different meanings. The one surrounding vectors will mean the length. But you can actually distribute your modulus over the K and the A. When you have modulus of Ka, you can distribute the modulus. Okay. Next, a scalar product, section 9.2. So now we are entering the second half of chapter 9A. Still a long way to go in vectors because we still have chapter 9b and also FP1 vectors. Scalar product. First of all, let's learn how to compute scalar product. This is a new concept to many people here. So when you have two vectors, it will be easiest to understand if I demo to you using a numerical example. If I have a vector 1, 2, 3, dot with a vector -2, 5, and 7. This has nothing to do with matrix. This has nothing to do with matrix. These two are vectors. These two are vectors presented in the bracket form. And we are not touching any matrix here. So scalar product is an operation that converts two vectors into a number. This dot is not a usual multiplication. And never write the dot as a cross. Never write a dot as a cross when dealing with vectors. Be very careful about vectors because there is another thing known as vector product. A dot B and A cross B are totally different. When you have vectors, these two are totally different. If you have numbers, then it doesn't matter. Like 5.2 is equal to 10, 5 times 2 is equal to 10. When you have usual numbers, it doesn't matter. But when you have vectors, be very careful. Dot and cross have totally different meaning. And if you write nothing in between, then people will not know whether you want the dot or you want to cross it. So for vectors, be very careful. Now, so a scalar product is an operation that uses two vectors as an input. It operates on two vectors and it converts it to a number. So how to convert it? You just multiply the corresponding numbers in every component. So you have 1 times -2 plus 2 times 5 plus 3 times 7. And you just compute as usual. This is -2 plus 10 plus 21, and you will get, I believe this is 8 plus 21, that's 29. Okay. So you end up getting a number, not a vector. Okay. So it takes in two vectors. The dot product is an operation that takes in two vectors. You have a vector dot with a vector, it gives you a scalar. Vector dot vector equals a scalar. And this, that's why we call this a scalar product, because it generates for you a scalar. We call this a scalar product. It is more common for us to call it a dot product, because the symbol for scalar product is a dot. Later in FP1 syllabus, we will learn another thing known as a cross product. But for now, I'm not going to mention the cross product yet. We will learn it eventually. Just very careful when you want to compute dot product. The dot must be written. The dot must be written and never replace it with a cross. I repeat, never replace the dot by a cross. If you write nothing in between, nobody would know what is happening here. So don't leave nothing in. Don't write nothing in between. Don't leave it empty. You either write a dot or a cross there, depending on what operation you intend to do. Okay. So also the term scalar product, do not confuse it with scalar multiplication of vector. Earlier in chapter 9A, on page 3, I think. Yeah, on page 3, we have the term scalar multiplication. Scalar multiplication means we are multiplying a vector by a number. Like a becomes 2a. We take 2 multiplied by a, where a is a vector. Right. So don't confuse scalar multiplication with scalar product. They mean different things. So to avoid this confusion, I usually like to call scalar product as dot product. Okay. Point number 2 gives you an alternative formula to compute scalar product. It will also generate for you a number. Point number 2 says that A dot B can also be computed by using modulus of a vector. A and B are printed in bold, so A, B are both vectors. Okay. So this means A dot B is equal to length of vector A times with length of vector B times with cos of theta, where theta is the angle between the vectors A and B. Okay. Now be very careful with the angle between two vectors. The angle between two vectors, there is a very strict way of where to identify the angle. You need to know where the angle is located when you talk about angle between two vectors. Okay. So the rule or the guideline to use is angle between vectors A and B is the angle measured between the two vectors when the vectors are either converging or diverging. But this is a very strict requirement. No compromise on this. When we talk about angle between two vectors, it is always the angle formed when the vectors are converging or diverging. Okay. The first diagram, okay, so if I call this vector A and call this vector B, then we say that A and B are diverging. In my first diagram, A and B are diverging. In my second diagram, if I call this vector A and I call this vector B, this is a case when maybe I shouldn't use A and B because the directions are different. Let's name it C and D. Okay. But this is a case when the vectors C and D are converging. So we always measure the angle between two vectors when the vectors are diverging or converging. Okay. Diverging means they point out. Diverging means point out from a common starting point. Converging means point towards a common ending point. Now, if you are given a pair of vectors, let's say E and F, if I give you E this way and F this way, if you take this to be the angle between them, it will be wrong. This is not the angle between E and F. So be very careful. Because in this purple colored diagram, my E and F, they are not converging, they are also not diverging. So you cannot measure the angle between them just like that. You cannot measure it like that. So if the question still wants to ask about angle between vectors E and F, what we should do is we move one of the vectors. We move one of the vectors such that they become diverging or converging. Remember, vectors are free. Vectors can always be moved around. So we are going to move, let's say I move the vector f. Okay. So I'm going to move the vector f while my E remains unchanged. My f, I move it down here, maintaining the length and direction. So if I move my vector f down here, then now I can happily measure. This is the correct angle. This is the correct angle. Okay. If I don't want to move my f down here, I can also move my E up. So I can keep my f at the original position, but my E, I move it up here. Yeah, then you will also get the same angle. If you maintain, so what I mean is this thing, you can also move it up. such that you place it here. And then you can take this as the correct angle data. De Hong asks, this is considered as diverging. Yeah, according to your diagram, your A and B are pointing out from a common point. Yeah, so you can take your angle to be that theta. Okay, so okay, something similar to the diagram sent by De Hong there. If my vector A is as long as what I draw here, and if my vector B is also as long as what I draw here, can I take this angle as theta? Actually, we can, because we can always reposition the vectors A and B. Let's say I move my vector A, I move it such that A starts from here. Okay, I maintain the length and direction. Okay, such that now this blue line becomes my A. Okay, so my two blue lines are of course parallel to each other, because the direction is maintained. Right, so by properties of parallel lines, you can always transfer your theta over here. So this theta is the angle when A and B are diverging, and it happened to be the same as this theta. Yeah. Right, so the two theta that I labeled there, they are the same angle. They will have the same size. Jindra asked, what if you put negative at F so that it points to the other direction? Okay, so okay, maybe I just show you a different diagram. Okay, if this is my vector G, and my H points this way, right, now they are diverging, G and H are diverging. So this is the correct angle theta. This theta is obtuse, this is obtuse and is the correct angle. Right, so angle between G and H is obtuse. So if you leave your answer as obtuse, is correct, and you are not supposed to convert it to acute angle. If the angle is obtuse, you leave it that way. If the angle is obtuse, you leave it that way. It would be wrong if you take this alpha here. This is wrong. If when the vectors are diverging, you get an obtuse angle, then your answer is obtuse. You leave it as an obtuse angle. Okay. Clifford asked in chat, we can also transfer our data to the right. What do you mean by data? I don't get what you mean by data then. Okay, you mean the line A. Oh, you're referring to this diagram, but if you move your line A to the right, okay, make sure you move it such that it becomes, okay, if you move your A and place it here, it will be wrong, because B and A are not converging. They are also not diverging. Yeah. If you place it down there, then it's okay. Yeah, this one is okay because it's converging. And so you can take your angle theta here. This will be a correct angle. Jendra says, if they are neither diverging or converging, would it be correct if I make one of the vector point the other direction? No, you never change the direction of the vector. You never change the direction of the vector. The concept of free vector tells us you can move the vectors around, but length and direction must be maintained. You never change the direction. Also notice that whenever I move my A around in my current diagram on the screen, the direction of A is always maintained. I never make it reverse direction. Never change the direction of vector. Okay, point number 3, the scalar product A dot B is a scalar and not a vector. Okay, so A dot B will give you a number and not a vector. Point number 4, properties of scalar product. Okay. Scalar product is commutative. Whether or not you have heard before, the word commutative is not important. A commutative simply means you can interchange the order. A dot B is the same as B dot A. Okay. Now, why is this so important? Every time we learn a new operation, we have to first study whether is it okay for us to interchange the order of the terms involved. Okay. To those who have learned before matrix, I know not everyone have learned matrix before. In matrix multiplication, matrix A times matrix B is not the same as BA in general. And so every time we learn a new operation, the first thing that we're interested to know is, does that operation allow us to interchange the order of the terms? Yeah. If you have never heard before about matrix, don't worry. We are not learning matrix now in this chapter. So here, this property tells us that when you have A dot B, it is safe to write it as B dot A. It's always safe. So this is a useful thing to know. But later, when we learn cross product, right, A cross B is actually not the same as B cross A. Yeah, but now we are not touching this line. Okay. So for now, we only need to know A dot B is the same as B dot A. It is safe to interchange the order. Part B says, let lambda be a real number or a scalar. Then lambda A dot B is the same as lambda times A dot B is the same as A times lambda B. So what it means here is this. It is property A followed by property B. Okay. So property B says, if I give you a numerical example, if I have 3A dot with B, it's the same as 3 times A dot B. It's also the same as A dot with the vector 3B. But this is also a useful property. The scalar of 3, you can move it around. When you compute dot product, you are allowed to move the scalar around. Whether you want to stick your 3 with A, you stick your 3 with B, or compute A dot B first, then only multiply by 3, they all are the same. Property C says scalar product is distributive in the sense that it works like the usual way when you would multiply a number over a sum. Well, De Hong asks, is writing 3A dot B okay instead of bracket 3A dot B? Yeah, it's actually okay because it doesn't affect the meaning. It doesn't affect the meaning. If you write 3A dot B, it will be understood as 3 times A dot B. Yeah. It doesn't affect the final result, so it's fine. It's fine. Although I would still advise you to put brackets here. If you don't put brackets, I would say it's still fine. It's still fine because no matter how you interpret it, whether you interpret 3A this way, or you interpret A dot B first, it won't affect the final result. But I will still advise you to put brackets if you can remember. Okay. So part C is telling us if you have A dot with B plus C, if you have a sum, then you have A dot with the sum. A dot can be distributed over to B and C. So you have A dot B plus A dot C. Hey, don't forget to write your dot. Don't, don't forget to write your dot. The dot needs to be there. Next. Okay. Poor Nation asks, what exactly are we finding in graphical terms when we get the scalar product of two vectors? Well, we are not learning the graphical interpretation of scalar product in our syllabus. We are not learning the graphical interpretation yet. And so I wouldn't want to talk about it. Okay. So our syllabus only requires us to know that when you take two vectors and dot them together, you end up getting a number. Okay, so what does that number, what is the use of that number? Okay. Later on the next page, we'll learn how to use that number. If the number happens to be 0, then there is a very useful thing that we can deduce. The two vectors will be perpendicular if the dot product is 0. Yeah. And so this is one of the major uses of scalar product. If a scalar product is a non-zero number, our syllabus doesn't require you to know the graphical interpretation of it. We will use it to we will use dot product to find angle. That's another major use. But the interpretation of the non-zero number itself, you do not need to know. The picture posted by Rongjie there, that one is not in our syllabus. Yeah. So don't have to worry about that. We are not learning that in our syllabus. Right. Moving on to point number 5. Scalar product involving parallel vectors. Okay. Remember that parallel vectors means there are two possibilities. The pair of vectors can have same direction or opposite direction. There are two possibilities, and here we are going to study the two possibilities separately. Okay, so here they say if vector A and vector B are in the same direction, one can be longer than the other. And they just say same direction. So you will end up getting 0° as the angle between the two vectors. Okay. So if my A and B are drawn like this, so in my current diagram, A and B are not diverging. But I can always move my A. I can always move my A. Such that it shares the same starting point as my vector B. Then you will see that my A and B will overlap. At least part of A. Part of A overlaps with my B. And so when the two lines overlap, what is the angle between them? It will be 0°. Angle between A and B is 0°. Okay, so applying the alternative formula, modulus A modulus B cos theta, where your theta is 0°, and what is cos of 0? Cos of 0 is 1. Okay, so you end up getting length of A times length of B only. Okay. If you ask me, do we need to memorize this box here? I would say you don't really have to memorize. And because once you are aware that the angle between them is 0, you can easily get this result. Right, so you don't really have to memorize this result. Okay. The one that I suggest you to memorize will be the next one. Okay. In particular, if you take a vector dot with itself, a dot a. Okay. If this is a, then of course, if I draw a one more time, it will look exactly the same. Same direction and same length. Now, what if I move my first a to the second, such that they are diverging? Then I will have exactly two lines overlapping each other. And so what's the angle between my first A and my second A? Of course, angle between them is 0. Angle between A and A is 0. Right, so if you have A dot A, according to the alternative formula, you have length of A times length of A times cos of an angle between them. Here, the angle between A and A is 0 degrees. And because this is actually just a 1, you get length of A squared. And so this is a useful result, and I suggest you to memorize. Okay. Any vector dot with itself is just its length power 2. It should say in chat, scalar product of parallel vectors is just the product of their magnitudes. Not exactly correct. Scalar product of vectors in the same direction. Same direction is more specific than parallel. And because parallel got two possibilities. Length of A times length of B is only true when A and B are in the same direction. Parallel is not enough. Huh? You need a more specific condition. You need same direction. A parallel is not enough. Okay. Now, the final note down here, I dot I equals J dot J equals K dot K equals 1. Okay. Can you explain why? The reason behind is very easy. Okay. I is a standard unit vector. This is actually 1, 0, 0. And everyone knows the length of I is 1. Because it is standard unit vector. Length of I must be 1. Right, so what is I dot I? I dot I will be just length of I squared, which is just 1 squared, which is just 1. And you can do similar things to J dot J. It's length of J squared, length of J is 1, 1 squared is just 1. And same goes for K dot K. Length of K squared, 1 squared, 1. That's it. Okay. Move to the next point. When A, B are in opposite directions, cos of 180 is negative 1. Cos of 180 is negative 1. This is negative 1. And that's why you get negative of length of A times length of B. Okay, when A, B are in opposite direction, it's easy to visualize a diagram. And so if this is my vector A, my vector B could be pointing the other way. And if I make them diverging, I can always move my A down here, such that my A points this way. Then angle between them must be 180 degrees. And so applying the alternative formula, you get cos of 180, which is minus 1, and then you are left with just negative of length of A times length of B. Okay. Okay. Do we need to memorize this formula? I think you don't have to memorize, because you can easily obtain by realizing that angle between two vectors with opposite directions is 180 degrees. Once you're aware of the 180 degrees, you just need to sub into alternative formula. Then you will get this result easily. So out of the 3 boxes here, under point number 5, the only thing that I suggest you to memorize will be the box in the middle. The other 2 boxes, you don't really have to memorize. Okay, now move to application of scalar product. Okay. This is a very common use of scalar product in an exam question. They will ask you to find angle between two vectors. Okay. So according to the alternative formula, we know A dot B is length of A times length of B times cos theta. Then if you make cos theta your subject, it will be A dot B divided by length of A, length of B. Then theta will be just cos inverse of A dot B divided by length of A, length of B. It is okay to use the cos inverse notation here. It's okay to use the cos inverse notation because if the term in the bracket happens to be a negative value, cos inverse function will generate for you an obtuse angle, and that makes sense. So it's actually okay to use the inverse cos notation here. Okay. Also, in an exam question, if the angle has a name, then you don't have to use theta. So for example, if question asks you to find angle ABC, a simple visualization, angle ABC will be this one here. Okay. To ensure that you get a pair of diverging vectors to dot, one very easy technique is just by looking at the name of the angle, you take the middle letter, point to each of the two sides. Okay, so BA and BC. Vector BA and vector BC will enable you to get the required angle. Okay, because in the diagram, BA and BC are diverging. Okay, so this is one very easy way to get a correct pair of vector. So you would form an equation by saying cos of angle ABC is equal to vector BA dot vector BC divided by length of BA, length of BC. And then you can proceed with a computation, and at the end, you solve for angle ABC in degrees. Okay. If the angle already has a name, then you don't use theta. If you write cos theta equals to BA dot BC divided by length of BA, length of BC, and at the end you get theta equal to something. If you don't tell me what your theta means, I will pretend that I don't know where theta is. Because in a diagram, there are so many angles that can be formed. So how can you expect the examiner to know what your theta refers to if you don't tell them clearly? Right? So just don't introduce theta unnecessarily. If it already has a name, you just use the name of that angle. If you insist on using theta, you can use theta provided that you first say let theta equals angle ABC. Then only people will know that your theta actually is used to represent angle ABC. Right? But introducing an additional symbol there is just unnecessary. Just don't do unnecessary things. Okay. Right, the second use of dot product or scalar product is to show that two vectors are perpendicular. So it's very common. It's very common in an exam question. They may ask you show that, let's say, AB is perpendicular to CD. Okay. So in the diagram, you can have something like this. Okay. So the diagram could be like this. You can have AB here and CD here. And so they want you to show that AB and CD make exactly 90 degrees here. Okay, so one very easy way to show this is you would construct a vector using points A and B. Okay, so you can construct a vector, let's say vector AB. You will also construct another vector using C and D. Okay, and after some computation, if we are able to get a 0, then you can then happily conclude vector AB is perpendicular to vector CD. Okay. Hence, the line AB is perpendicular to the line CD. Notice that the 0 should appear at the end. And the result that you wish to show should appear at the end. 0 should not appear too early. This is obtained via computation. Okay. So can we use a different pair of vectors to show? If I don't like to use vector A, B, and C, D, I can also use a different pair. As long as I have a vector formed from using points A and B, so I can actually take BA.CD. If I can show BA and CD are perpendicular, then of course the lines AB and CD are also perpendicular. If I don't like to use CD, can I use DC? Also can. Yeah. So if these two red color arrows are perpendicular, then of course the two blue lines are also perpendicular. Right. So you have a bit of flexibility here in terms of the vectors used. As long as one vectors involve points AB, the other vectors involve points CD, then you just dot them together and hope to get a numerical value of 0. Then you can happily conclude that the two vectors are perpendicular. And then of course, if you use vectors BA and DC here, then over here you of course have to state BA is perpendicular to DC to be consistent. Right. Yeah. So the thing to remember here is you have an if and only if relationship. Right, so if A is perpendicular to B, their dot product must be 0. Same for the reverse. If the dot product is 0, then the two vectors are perpendicular. Okay. Then there is this small note here at the bottom of the box. I.j, j.k, k.i, they are each equal to 0. Can you explain why? It's easy. It's because I and j are perpendicular. J and k are perpendicular. K and I are also perpendicular. You can easily see from the 3D diagram here, x-axis, y-axis, and the z-axis. Y-axis is here. Y-axis is here, z-axis is here. Okay. Here's my vector I. Here's my vector j. Here's my vector k. And so obviously I and j are perpendicular, j and k are perpendicular, and I and k are also perpendicular. And because you have a 90 degrees here, a 90 degrees here, and also a 90 degrees here. Okay. Next, example 9 is just a very quick practice on how to compute dot product. Here I'm using a two-dimensional vector for you to practice on. In the exam, 99.99% of the question will give you 3D vectors. Okay, so this example 9 is just for you to warm up. Wait, I think I opened an older version of the notes. Yeah, the notes that I upload for you guys, I believe it looks a bit different. Wait. Oh no, it should be P3 notes. Yeah, this is the latest version. This is just for you to practice on. The vector R1 is 2, 1. Vector R2 is 1, -3. Then what is R1 dot R2? This is part A, R1 dot with R2, 2, 1 dot with 1 minus 3. Okay, when you write your working, don't give me just a single number. Don't just give minus 1 straight away. That is too fast. That is too fast. I don't accept that. And method marks are given for correct method used to compute. Right? So you have to show a bit of steps. Okay, so what you need to show is you need to show that you are adding up two numbers. 2 times 1 give you 2, you can write 2 straight away. 1 times minus 3 give you minus 3, you can write minus 3 straight away. So as long as I see that you are adding up two numbers, I regard this as method. Okay, so method mark given for this. If you want to be even slower and write 2 times 1 plus 1 times minus 3, of course, also can. But at the very least, I want to see 2 minus 3. So make sure don't be too fast. When you present your working, don't be too fast. Okay. Then for part B, R1 dot with R2 minus R1. R1 dot with R2 can sub in. Minus R1. R1 is 2, 1. Oh, in fact, the R1 we can also sub in the numbers already. 2, 1 dot with. Okay, now in my square brackets, I can compute it so that it becomes just a single vector. This is minus 1 minus 4. Okay, then next you will have to write minus 2 minus 4. That gives you minus 6. Just continue on the right here. Then R1 plus R2 dot with R2. Then by R1 plus 1 minus 3 dot with 1 minus 3. Compute the vectors in the square bracket. You have now 21 and 7 dot with 1 minus 3. 21 times 1 is 21. 7 times minus 3 is minus 21, and you get 0. So at least I want to see 21 minus 21 when you compute the dot product. Okay. For part D, the question there, they write 3R1 dot R2. It's not very clear whether the 3 is stick together with R1 or is it 3 multiplied by R1 dot R2. So as I mentioned just now, whether you stick your 3 with R1 or you isolate your 3 at the outside, it doesn't affect the final result. To make it clearer, it's actually better to use some brackets and to make it clear whether your 3 is isolated at the outside or is it sticking together with R1. So for question D, I would like to change the question a bit. I will add another layer of bracket here. 3R1 dot with R2. Then followed by R1. Yeah, so let's change the question here. So that the meaning is now clearer, although it doesn't really affect. It's actually better to make the meaning clear. Okay, now let's do part D. 3R1 dot with R2, then followed by R1. There's no dot here, there's no dot in front of this R1. It's supposed to be no dot there. If you write a dot, it will become wrong. Why? Because 3R1.R2, this bunch will give you just a number. So when you have a number times R1, you don't need a dot there. Now let's do the computation. 3 times R1. 3 times R1, R1 is 21. And then this thing dot with R2, R2 is 1 minus 3, followed by the vector R1 is 2, 1. Now we have 6, 3 dot with 1 minus 3, 2, 1. 6 times 1 is 6, 3 times minus 3 is minus 9, 2, 1. So now you have negative 3, 2, 1. Negative 6, negative 3. Done. Okay, we'll do one more example, then we take a break. I prove that the diagonals of a rhombus are perpendicular. This is a general rhombus, and they are not giving you any specific rhombus. This is a general rhombus. So you have to prove that this statement is true for all rhombus. Okay. So in order to prove this, you will want to introduce a diagram. So there are actually many ways to prove that the diagonals of a rhombus are perpendicular. Here in the vector chapter, let's try to do it the vector approach. Okay. Now, let's draw a rhombus first. This drawing will be part of our working. Let's just draw a random rhombus. The main property about rhombus is that the 4 side lengths must be equal. Now let's name the vertices of the rhombus. So you can name it A, B, C, D, P, Q, R, S, or whatever you like. Here I will just call it O, A, C, B. You can name it however you want. Okay. So okay, it says let OACB be a rhombus. Okay, when you name a parallelogram, the naming should be done in a circular sequence. OACB. You can also name it OBCA as long as it's circular. Okay. Now I want to introduce some small letter vectors. The way I draw it, it should be OACB. The way I draw it, it should be named as OACB. If you want it to be OABC, then you will draw it like this. It's OABC like this. What I mean by circular is that in the naming, in this particular yellow colored word, the yellow colored word, the vertices should be named in a circular order. Yeah, the way I draw it, I intended it to be called OAB, OACB. I intended it to be called this way. Okay. Now I want to introduce some small letter vectors, okay, for easier proving later. Now I let OA be the vector A. Okay, I let OB be the vector B. Okay. You can of course also let OC be the vector C, but I'm not going to introduce the small letter c because I want to minimize the number of small letter vectors involved. Okay, I just introduce small letter A and B. So A points this way, B points this way. Okay. Now, where are the two diagonals? The diagonals will be the dotted lines in green. Okay. They want you to prove that diagonals are perpendicular. So what you need to show is that the vector AB dot with the vector OC is equal to 0. That's what you need to show. If you can show AB dot OC equals 0, then the next step you can conclude the lines AB and OC are perpendicular, and therefore diagonals of rhombus are perpendicular. Okay, so now let's try to get AB and OC in terms of the small letters A and B. AB is OB minus OA. Okay, that's vector B minus vector A. Okay, then what is OC? OC will be, take a convenient path, OA plus AC. Okay, but then I don't have a small letter for my vector AC. Recall that OB and AC are actually parallel in a rhombus. Okay, a rhombus is a special form of parallelogram. So AC and OB are guaranteed to be parallel. Okay, and from the way I draw it, AC and OB points in the same direction. Since AC and OB has same direction and same length, I can happily replace AC by OB. Okay, because AC and OB are equal vectors. Equal vectors means same direction and same length. Okay. Then I can write this as A plus B. To ease my computation later, I will just rearrange and write as B plus A. To ease my computation later. Okay. Now it's time to dot them together. AB dot with OC. Okay, that will be B minus A dot with B plus A. Okay. B dot with B. Okay, this one, sorry, I should do it in a more systematic way. Okay. Then B dot with A. Okay, then next, negative A dot with B. Negative A dot with A. So it works in a way that is similar to the usual multiplication. It works in a way that is similar to the usual multiplication. The only difference is that you have to write a dot in between for every term. Okay. Then what is B dot B? From the previous page, we know a vector dot itself is the length of the vector square. Okay. B dot A, I will just keep it that way. A dot B is the same as B dot A. Dot product is commutative. In the previous page, we learned that. And then A dot A is length of A squared. Right, now you have these two terms cancel each other. Then we are left with B squared minus A squared. Length of b squared minus length of a squared. What is our aim? Our aim is to get an answer of 0. Okay. So, how can we justify? How can this be 0? How can we justify? Oops, okay. Yeah, how can we justify that this is actually 0? Yeah, the length are the same. Yeah, the length are the same. Right, so if you write 0 straight away, it will be too fast. You have to justify a bit. Yeah. Okay. So one way to justify this is I replace length of A by length of B first. So in my next step, okay, then here I say because length of vector A is equal to length of vector B. So this will be a good enough justification. Length of vector A is the same as length of vector B because all sides of a rhombus have the same length. And vector A is actually a side of a rhombus. Vector B is also a side of the rhombus. So although the yellow and the blue, they are pointing in different directions, but they have the same length nonetheless. So length of A is the same as length of B. That's why we can happily replace length of A by length of B. And the power 2 remains, of course. Okay. Then you have now length of B squared minus length of B squared is the same thing, minus by itself. That's why we can happily get 0. Okay. Since AB dot OC is equal to 0, AB is perpendicular to OC. Therefore, the diagonals in the rhombus are perpendicular. Right, so this is a way to prove that something, I mean, a line is perpendicular to another line. We are making use of the dot product. When dot product is 0, that means the two vectors are perpendicular. If the two vectors are perpendicular, then of course the lines used to form the two vectors are also perpendicular. So notice that here, when I have arrows above, when you talk about dot product, when you use the dot, the two things involved at the left and right of the dot must be vectors. But when you talk about perpendicular, it's actually also correct if you say vector AB is perpendicular to vector OC. It's also correct. But what we are more concerned about is only the line AB and OC. Right? So when you talk about perpendicular, you can say two lines are perpendicular. You can also say two vectors are perpendicular, depending on your need. Right? So here we are more concerned about the lines AB and OC, and not so much about the vectors. Right? That's why when I mention this sentence in green, I remove the arrows from AB and OC. Because I'm more concerned about the lines, not so much about vector. But when you talk about dot product, when you involve dot product, AB and OC must have arrows above them, because dot product can only operate on vectors. If you write AB dot OC equals 0, this will be a wrong statement. Because a dot product can only operate on vectors. So be careful with your way of writing things. And when you need an arrow above, when is it optional to have arrows above? Kushagri asks, are we allowed to label all sides as vectors since we know all sides are equal? But if you want to label, like if you want to call this vector E, you want to call this vector F, of course there's nothing wrong. But then it will make your cancellation a bit more troublesome. When you consider the dot product, right? If you involve, okay, so if you do it this way, then when you take OA plus AC, you will get vector A plus vector E. And then when you have the dot product later, you will have B minus A dot with A plus E. The cancellation will be a bit more troublesome. Oh, Kushagri mean all A. No, you cannot put it all A. You cannot. That is definitely wrong. If you call this A and you call this A, straight away is wrong. Different direction. Different direction. And so it's definitely wrong. Right? A vector comes with length and direction. To claim that these two are the same, you have to ensure that these two are the same length and same direction. Okay. If you want to call this side as A and this side as A, then it's okay, because they indeed have same length and direction. Okay, but if you want to call this one as A, no way. Okay. Yeah, Clifford asks, can all be the length of A? Well, first of all, if you name it the way I name it, then of course you would refer to this length OB as the length of B already. Then OA will be the length of A. Then you can say length of A is equal to length of B. This will be a better way to present. In your diagram, you should label the vectors with direction. You don't only label the length. Of course, I know the length of all four sides are the same as the length of vector A, I know. But then when you label your diagram, the vectors should come with direction. Is the diagram part of the working in this question? Yes. In this question, yes. Or else it's hard for the reader to follow what you're doing. Okay, let's take a break now. When you come back, we'll continue with example 11. I start the timer. Diraj asks, when I sketch a diagram, must the length be accurately equal or no need? The diagram needs to be drawn, but it doesn't need to be 100% accurate. It's only a sketch. A sketch doesn't need to be 100% accurate. Okay, you'll come back in 7 minutes. I've started the timer. Hi everyone, welcome back. We have about half an hour left. We can cover at least 2 or 3 more questions, hopefully. Okay. Now we are at example 11 on page 12. For example 11, you have ABC are 3 points. This is still a 2D question. Just to warm you up, in the exam questions, it's definitely a 3D question. They won't be so kind to give you 2D. But anyway, just to practice on it, we are given AB as 2, 1, BC as 1, 3. They want you to find angle ABC. Okay, the two vectors that you need, be very careful to get the correct vectors. Okay, it's not AB and BC. It should be BA and BC. Okay, you start from the middle, you point to the two sides. The vectors you need are actually BA and BC. And so if you take A, B, and BC, it will give you the wrong answer. And so be extra careful. And if you really visualize the angle ABC, just draw some random diagrams there. Yeah. ABC can look like this. To make sure that you get a pair of diverging vectors, you need BA and BC. Okay, so the first thing to do is actually to get the vector BA. BA is negative of AB, and that should be negative 2, negative 1. This one should be obvious. Okay. Then next you can find cos of angle ABC. Is equals to BA dot BC divided by length of BA, length of BC. Okay, I suggest you to state this formula. Okay, I wouldn't say it's a must to state this, but I suggest you to state this so that you can make sure that you are using a correct pair of vectors. Also make sure that your vectors are, the vectors involved here are BA and BC, which you can easily identify by starting from the middle, point to the two sides, B to A, B to C. Okay. Then only you submit the values. Minus 2 minus 1, dot with BC is 1, 3. Divided by length of BA, you can apply the length formula straight away. And then when you compute the dot product, remember, don't give me a single number too quickly. Show that you are summing up two numbers. So it's minus 2 minus 3 up there. And then at the bottom you have square root 5 and square root 10, and you have minus 5 over cert of 50. Okay. Whether or not you want to simplify this fraction further is not important because you're about to take the inverse cos anyway. Right, so okay, the usual way to solve one angle, like if you have cos of theta equals minus sec 5 over, minus 5 over sec 50. Oh yeah, one more thing that I think I didn't mention in the notes earlier. Okay, is that, yeah, I think I didn't include in the notes. The angle between two vectors is always between 0 to 180. So maybe you should add this on to your notes there. Theta is always between 0 to 180 degrees. And this is always inclusive of 0, inclusive of 180. Okay, because when you have two diverging vectors, and no matter how you draw the diagram, if you have A like this, B like this, it's always possible to form either an acute or obtuse. It's not wrong to take the larger one, but we always take the smaller one. It is common practice to always take the smaller one. So it is always possible to find an angle between two vectors to be either an acute or obtuse angle. It is never larger than 180. Because if there is a very big reflex angle, there is definitely another smaller one, and we always take the smaller one. Right, so let me go back to the working up there, the part in green on the right of your screen. And so if you need to solve such an equation, usually what we'll do is we'll find basic angle. By pressing the calculator, we find cos inverse of 5 over sec 50. And then you would get the basic angle of, let me press it, cos inverse of 5 over sec 50. Then you get, okay, this happens to be 45 degrees. Okay. Now, then you would consider your ASTC diagram. Here we only look at the first two quadrants. We don't care about third or fourth quadrants because the angle between two vectors is guaranteed to be either a quadrant 1 or quadrant 2 angle. Okay. Then cos is negative in the second quadrant, 45. Then you would get this being 135. Yeah. Okay. So this is the usual way we would solve for the angle. But since we are taking inverse cos, at this time, since we are taking inverse cos and we are guaranteed to have our answer in either the first or second quadrant only, then you can actually conveniently include the negative into your calculator, because if you press your calculator, cos inverse of minus 5 over sec 50, your calculator will nicely give you 135. The inverse cos function is able to give you answers in the first or second quadrant. If the number that you key in is positive, it's definitely acute. If it's negative, it's definitely obtuse. Right, so when you take inverse cos when finding angle between two vectors, you can just conveniently press cos inverse of this fraction. If it's a negative number, you can actually key in the negative. Because you're guaranteed to get only one solution, and you are not using the basic angle to generate solutions in quadrant 3 or 4. So it doesn't matter if you don't get a cube. If you get an obtuse, the answer will be just obtuse. So this is a bit different from what we usually do in the trigo chapter. In the trigo chapter, I always tell you guys to make sure that your basic angle is acute, because you might need to find a solution in possibly the third or fourth quadrant. So you will need your basic angle as acute to facilitate in that process. But over here, we don't care about solutions in third or fourth quadrant, so you can just press cos inverse straight away. It will give you 135. And that's it. Okay, remember when you press cos inverse, remember to change your left hand side of the equation to angle ABC without the cos. Okay, so that's the answer for example 11, and I move to example 12. The position vectors of E and F. So you are given OE as 2, 3, minus 5. OF as 3, minus 2, minus 1. Oh, can scroll up a bit. Find the angle EOF. Okay, so from the name of the angle, even without visualizing any diagram, you know what are the two appropriate vectors to get. Okay, from the name of the angle, you know you start from the middle, O towards E, O towards F. This is guaranteed to be diverging from the angle that you want. Right, so you will need OE and OF, which in this case is already provided. So that's good. Right, so let's just find cos of angle EOF is OE dot with OF divided by length of OE, length of OF. Okay. Then sub it. Okay, when applying the length formula, also you need to show your method. Don't just give me the length straight away. I want to see square root of 2 squared plus 3 squared plus negative 5 squared. Third of 38, third of 14 down there. At the top you have 2 times 3 is 6, 3 times minus 2 is minus 6, minus 5 times minus 1 is plus 5. It shows that you are adding up 3 numbers. And then it's just 5 divided by third 38, third 14. And whether or not you want to multiply your 38 and 14 together is optional because you are about to take inverse cos anyway. Right, so just take cos inverse of this fraction. That will give you EOF. 77.5 degrees to 1 dp. That's it. The final answer rounded to 1 dp. Earlier, the 135 for the previous question, there's no need for a 0.0 there because that was an exact value. Okay, next we have part 2. Right now you are given that vectors G and H are perpendicular, which means you can use the information that G dot H is equal to 0. This is not a show question. Now they tell us G and H are perpendicular, so we can safely use the information G dot H equals 0. Okay. Your vector G is this 8C minus 2, vector H is C minus 3 minus 1. So you are given that G is perpendicular to H. This means vector G dot vector H is equal to 0. And then just solve this equation, opening up the dot product. C is minus 2 over 5, and that's it. Okay. Next is example 13. PQR have position vectors small p, small q, and small r respectively, and they also give you in terms of I and j. Okay, this is actually a 2D question. This is not a pass here, it's actually a 2D question. You see that they only involve I and j, there's no k. This is actually a 2D question. In the exam questions, it's definitely 3D. So this 2D is just for you to practice. Okay. Right, find the vectors PQ and RQ show that they are perpendicular. But this one should be easier because you already have OP here, uh, OQ and OR here. So to get the vectors PQ and RQ, just use the usual subtraction formula. O to the end point minus O to the starting point. 3, 12 minus 7, 10. RQ is OQ minus OR. To show that these two vectors are perpendicular, just dot them together, hope to get an answer of 0. PQ dot with RQ minus 16 plus 16 equals 0. Right, therefore, PQ is perpendicular to RQ. Get done. Okay, move to part 2. Okay, using scalar product or otherwise, find the angle PRQ. Okay, to find an angle in a vector question, we always use the scalar product method. Okay, although here they say otherwise, they actually allow us to use some other methods, but I think using scalar product is still easier. Okay. Okay, now the angle that they want to find is angle PRQ. Yeah. Find angle PRQ. Two vectors that you need are RP and RQ. Okay, do we have RP? Actually, we don't have yet. Okay. So let's find the vector RP. That's 8, 6. And then we have enough information now to apply the cos formula. Cos of angle PRQ is RP dot with RQ divided by length of RP, length of RQ. RQ, we have it earlier from part 1. Then the length formula at the bottom. 32 above 6 times 8 is 48. At the bottom, you have this 10 and square root of 80. At the top, it's actually 80 divided by 10 square root 80. Which you can simplify further as 8 over 80 if you like. Okay. Then angle PRQ, you just take inverse cos of this fraction. That will give you 26.565 degrees rounded to 26.6 degrees 1 dp. Okay, why am I writing a longer decimal here before I round is because this answer will actually be used in the later part. And this is only part 2 of the question. So there is a possibility that this value will be used later. So it's better to write a longer version before rounding. Okay. And in fact, this answer will actually be used later. Okay, part 3, this question doesn't require a diagram. If I just draw a diagram to visualize, it says S is a midpoint of PR. And find the position vector of S. Just apply the midpoint formula for vector. OS is half times of OP plus OR. This one should be very simple. It's half times of OP OR. Okay, done. They want position vector of S, so OS is already the position vector of S, and we can leave the answer that way. But if they ask for coordinates, then you have to convert into coordinate form. And here we don't have to convert to coordinates because they want position vector. Okay, part 4, show that the length of QS is equal to the length of RS. Okay, so now we have a position vector of S already. We have the vector OS. So before we compute the length, of course, we have to know the expression for the vector first. Okay, so let's compute the vector QS for part 4, which is OS minus OQ. 37, OQ is 312. That's 0 minus 5. And then length of QS, that's 5 units. Okay, then we also want to compute length of RS. Then length of RS is the usual length formula. If you forget to write the word units, it doesn't matter. For part 4, could we just use the midpoint formula? How do you use the midpoint formula to get the length? OS is half of... Wait, I don't get what you're trying to say there. S is the midpoint of P and R. Nothing to do with Q. So I don't see the logic. I don't see the logic about what you said. Oh, okay. Yeah, so let's carry on from here. Okay, so we have computed the vector OS and RS. We have also found their lengths individually. We notice that these two are equal. Okay. So therefore, we can say length of QS is equal to length of RS, which is equal to 5 units. And show. Okay, then they say using your previous results or otherwise find the angle PSQ. Okay. They say otherwise, that means they allow us to use a method that doesn't uses the previous result. And so if you want to use otherwise, then of course you can just use the usual scalar product method lah. Where cost of PSQ is SP.SQ divided by length of SP, length of SQ. You can of course do that. Okay, here, the method that I will show you is a method that uses the previous results. Okay. Okay, but honestly speaking, the previous result is not so easy to use for this question. Okay, it requires you to be to use the fact that S is the midpoint of P and R, and also make use of QS equals RS. The length of QS equals the length of RS. Okay. And it requires you to visualize the diagram in a somewhat accurate way, or else you can't see. So honestly, I will say using previous result is not easy. Okay. So you have your R minus 1, 4 here, S with the coordinate 3, 7, then P with the coordinate 7, 10. Yeah, something like this. And so if you want to be more accurate, your RSP should actually be sloping upwards, because the y coordinate increases. Then you have your Q here with coordinates 3, 12. So these are all information that we had earlier. From your vector OP, OQ, OR, and also OS, you can find the coordinates. Okay. And so Q will be directly above S because they have the same x coordinate. Okay. Then other than this few, so other than the coordinates, QS equals to RS means that this length and this length are the same. Then we also know that S is the midpoint of PR, which means this and this are also the same. Okay, maybe I should draw my line a bit slanted so that it's closer to reality. It should be like this. Yeah. And here's your P7, 10. Here's your R minus 1, 4. Yeah. Okay. Because S is the midpoint of PR, so SP and SR have the same line. Okay. Now, earlier we have found an angle. We have found an angle PRQ. PRQ is over here. It's this angle here, and we know it was 26.565. They want us to find angle PSQ, angle PSQ. This is what they want to find. Okay. Now, okay, I think everyone have heard before that when you have a triangle, with one of the sides extended, then this exterior angle will be equal to the sum of the two other interior angles. Right, so this yellow color angle will be the sum of the two blue angles. I think most of you have heard about this before. And this is just a basic property of triangle. Okay. So do we know the two blue angles? One of it is already available. The other one, you can just transfer this angle over because you have an isosceles. Alright, so making use of this, you should be able to get. Right, so angle RQS is the same as angle QRS. It's equal to 26.565 degrees. Okay. Because triangle SQR is isosceles. And then angle PSQ that they want, it will be angle PRQ plus angle RQS, which is 26.565 degrees plus 26.565 degrees, and in the end you will get the required answer of 53.1 degrees, rounded to 1 dp, and that's it. So this is the way to do it using your previous results. If you use the usual method of getting cost of PSQ using dot product, of course you can also do that, because this question allows otherwise. Okay. The time is already 3:01. I think I should stop here, and we'll continue tomorrow with example 14. And tomorrow we'll also start a new chapter, chapter 9B. I will upload the notes for chapter 9B later today. Right, that's all for today. Thank you, everyone. You may leave the video meeting.
Thank you, sir.
Have a nice day.
Thank you, sir.
Thank you, sir. Bye, sir.